This is part 4 of the stoichiometry notes. This is going to be mixed stoichiometry, so not just starting and ending at the same unit, so not just going from grams to grams or molecules to molecules, but we can kind of start and end wherever. We know we can represent any substance in terms of 3 units: mass, which is a unit of grams, moles, or molecules. And then we use the coefficient from our balanced chemical equation to write our mole ratio. And so with this, we can start and end wherever. Our problem might have us starting at moles of one substance and ending at molecules of another. Maybe we're starting at mass of one substance and ending at moles of another. And so we can use this kind of flow chart to help us guide what we're doing. With this, we really only have our 2 conversion factors still. 1 mole is molar mass. We also have, that was their first one, and then mole to molecules. And then we had added on at the beginning of these, writing that mole ratio. And remember, when we're setting these up, as we're looking at what goes on the top or the bottom of our conversion factor, what we need to get rid of goes on the bottom, and what we want to end up with goes on the top. And so that's how we are going to determine which part of our conversion factor goes where. All right, so now we are given a reaction. Notice it's a balanced chemical reaction. This is a decomposition reaction where we have potassium chlorate that is going to decompose into potassium chloride and oxygen. It's balanced for us. And if we look at this in number 10, if 5.45 grams of potassium chlorate are decomposed, how many molecules of oxygen are produced? And so with this, we are starting at 5.45 grams of potassium chlorate. So remembering that chlorate is one of those polyatomics, so we're going to be starting at that KClO3. That was our given. And this is asking us to find molecules of oxygen with that. So we're looking for molecules of oxygen. As we look at our chart up above, that means that we are starting at grams. So starting with that mass, that means substance A is our potassium chlorate, and ending with oxygen. And this one is ending with those molecules of oxygen. And so we are going to have 1, 2, 3 steps in order to do this. As we look at this and that setup, we start by writing our given. So writing out 5.45 grams of that KClO3, including our units and what chemical we're talking about, so we can stay organized. So in that first conversion factor, in order for us to go from potassium chlorate to oxygen, we have to get to moles so we can use our balanced reaction, which means I'm going to get rid of grams of my KClO3 because that's what's currently my unit in my given. And I need to relate these grams to moles using our 1 mole equals molar mass conversion factor. So we put grams on the bottom, which means 1 mole of KClO3 is going to go on the numerator. And then on the denominator, we need to find that molar mass. And so with that molar mass, we end up adding our 1 potassium, so 39.098, I'm looking at my periodic table, plus chlorine, 35.45, plus 3 oxygens, 15.999. And once I find that molar mass, that's going to go into my conversion factor down here. So adding that all up, I got 122.55. And notice that I have 2 digits after the decimal there, so I'm going to have 2 digits after the decimal, following my adding sig fig rules. If I was to stop here, my units for my answer would just be moles of KClO3. It's a one-step conversion, but we need to get to molecules of oxygen, which means I need to use that mole ratio from my reaction or from my equation. So I'm getting rid of moles of potassium chlorate. I want oxygen, so I need to first go to moles of oxygen. And I can look at my reaction now to determine what is that mole ratio. So I have 3 moles of oxygen in my reaction for every 2 moles of potassium chlorate. So then we will have 3 moles of oxygen over 2 moles of KClO3. Last step then is that we know, so that third conversion factor, we know that 1 mole is always 6.022 times 10 to the 23rd. That's Avogadro's number. And so to get rid of moles of oxygen, which is what I currently have up in here in the numerator, I need 1 mole of oxygen in the denominator, and then my 6.022 times 10 to the 23rd molecules of oxygen, which is the other part of that conversion factor, is going to go into the numerator. Once we have this set up, we use our units to make sure that we have that correct setup, making sure our units are canceling, and then I can go through and do my math. So I've got 5.45 times 1 times 3 times 6.022 times 10 to the 23rd, and I get 9.84597 times 10 to the 24th in my calculator, and then I need to divide that by anything in my denominator. So 122.55 times 2 times 1, and so we are dividing by 245.10, and then we get 4.017 times 10 to the 22. I need to look at my sig figs because this continued on in my calculator. So sig fig rules, we're looking at those values that we have in our work. So I have 3 sig figs in my given. This molar mass has 5 sig figs. Our mole ratio, these are exact numbers, so those don't contribute to sig figs. Avogadro's number is 4 sig figs. And so 3 sig figs is going to be our smallest, so we're going to keep 1, 2, 3 sig figs. So my final answer is going to be 4.02. Don't forget that times 10 to the 22. And then we need to include units and what chemical this is. Because if we're doing stoichiometry, we could be talking about any of the chemicals that are in our reaction. All right, let's do another one. If you are getting the hang of it, feel free to try it, pause and then try one on your own. If 5.45 grams of potassium chlorate are decomposed, how many moles of potassium chloride would be produced? And so this one, we're starting with that same 5.45 grams of KClO3, but now we're looking for moles of our potassium chloride, so our KCl. And so this one, instead of going all the way from grams to moles and then moles to molecules, we're going to have a 2-step conversion. We're just going to be stopping at the moles of our, in this case, potassium chloride is what our problem stated. So this is going to be a 2-step. Setting up 5.45 grams of KClO3. I have to be given some number. I'm just trying to look at what is the relationship or how much, how many moles of KCl, potassium chloride, will be needed to fully use up these grams. Getting rid of grams of that KClO3. We know we need to get to moles, so we can use that mole ratio. So 1 mole of KClO3 is that molar mass. We found that molar mass up here. Same thing as here. So that 122.55 grams of potassium chlorate in 1 mole. Now that I'm at moles, I can use the mole ratio in my reaction. I need to get rid of moles of KClO3. I want to switch to potassium chloride. So that's going to go in the top. And we get our values for that mole ratio from our reaction. So we're going to have 2 moles of potassium chloride for every 2 moles of potassium chlorate. Like that. And we don't need to simplify these ratios by seeing that 2 to 2. That way, that will simplify out in our work. And then we can go through, our units cancel, grams of potassium chlorate, moles of potassium chlorate, moles of potassium chlorate, and we can do that math. So we're going to have 5.45 times 1 times 2, which is 10.90, all over 122.55 times 2, which is 245.10. And then when we divide, we get 0.0447. And I can look, there's an additional 4 on there. And then I can look at my sig figs. 5.45 has 3 sig figs. Oftentimes it's our starting value that's going to determine that. My molar mass here has 5 sig figs. And again, these are exact numbers, so those don't contribute. So we're going to want 3 sig figs in our answer. 1, 2, 3. So I'm going to have 0.0445 moles of potassium chloride, or I could do 4.45 times 10 to the negative 2 moles of potassium chloride if I wanted to do scientific notation on that answer. All right, got one more example here. Hopefully you're kind of getting the swing of the setup, understanding how to set that up, following kind of the same ideas that we did in last unit. Feel free to pause, try this one on your own. How many grams of oxygen are produced? So we're looking for grams of oxygen when 3.3 times 10 to the 22 molecules of potassium chloride are produced. So even though these are both products, it doesn't matter. This is our given number. It doesn't matter if it's at the start of our reaction. And so we're going to have that 3.3 times 10 to the 22 molecules of potassium chloride. So that's KCl. And then we're going to go to grams of oxygen. So if we're looking at thinking of our steps, we're going to need to go molecules to moles of KCl before we can get to our moles of oxygen, before we can get to our grams of oxygen. So this is going to be 1, 2, 3 steps total. Or if we look up here, we are starting with molecules. We are ending with grams. And so that will be 1, 2, 3 steps for this conversion. All right, so let's go ahead and set up our work. I'm going to erase some of this stuff that we don't need. So 3.3 times 10 to the 22nd molecules of potassium chloride. And again, that's our given value, so that doesn't count as a conversion factor. Those 3 steps are going to be my 3 conversion factors that I use. Getting rid of molecules of KCl. Well, 1 mole, our goal is always to get to moles so that we can do a mole conversion using our reaction. Well, 1 mole of anything is 6.022 times 10 to the 23rd molecules, our Avogadro's number. Again, setting that up with the molecules on the bottom in order for those to cancel, the units to cancel. I'm at moles, so to get from KCl to oxygen, I need to use that mole ratio. So moles of potassium chloride, 2 moles of oxygen. I want moles of oxygen, so that goes on the top. I find the values for that from my reaction. So my moles of oxygen, here I have 3 moles of oxygen, and my moles of potassium chloride, 2 KCl, so a 2 on the bottom. All right, and our last step to get to grams. Now we're at moles of oxygen, so I need to get rid of moles of oxygen. Well, 1 mole of oxygen in this third step, 1 mole of anything is the molar mass. So 1 mole on the bottom, molar mass of oxygen on the top. Remember, oxygen is diatomic, and so we're going to have 2 times that 15.999 going to our periodic table in order to get the molar mass. And then plugging that in 31.988 into the numerator. Now that I have my setup, I can go through and do my math. 3.3 times 10 to the 22 times 1 times 3 times 31.998. I wrote this down wrong. And then we get 3.167802 times 10 to the 24th. I'm going to divide that by everything in the denominator. So that is 6.022 times 10 to the 23rd times 2, which is 1.2044 times 10 to the 24th. And then I can divide. All right, and I got 2.63019, and then that continues on. A good check to make sure, did I do this in my calculator correctly? These both have a times 10 to the 24th, so those should cancel, giving me an answer that is not in scientific notation. But let's go back up to our original work to look at sig figs. 3.3 is 2 sig figs. Avogadro's number, 6.022, is 4 sig figs. 31.998 is 5 sig figs, so we're going to want 2 sig figs in our answer. So keeping the ones place and the tenths place, so 2.6. And then I need my unit, grams, and then I need to say what chemical, O2. So 2.6 grams of oxygen is going to be our final answer. Reach out to your teacher with any questions. Good luck.